Okay, so there are two major types of isomerism. We have the structural and then the stereoisomerism. Under structural isomerism, we tackle the following. We have the chain, positional, functional metamerism, tautomerism, and ring chain isomerism. The major types of structural isomerism are the first three: the chain, which commonly occurs among alkanes; the positional isomerism. This exists if the structures differ due to the differences in the position of the functional group or differences in the position of the substituents. Pag sinabi namang functional, itong functional isomerism, the structures differ because both or three of the structures presented, they differ in the functional group. Okay, then for metamerism, tautomerism, ring chain, limited lang ni sila or rare types of isomerism. So nalang sila yung mga specific molecules kung asa sila ga-occur. Okay, then I had provided to you the pre-recorded lecture video for the first subtype of stereoisomerism, which is the geometric isomerism. Ayan. Okay, so sa geometric isomerism, again, if you recall, this occurs most commonly among alkenes. Okay, yung mga open chain alkenes. Okay, but you have to realize also nga ang alkenes, they may also possess structural isomerism. Okay, so kapag ang double bond differs in the locations, that shows structural isomerism, particularly a positional isomerism. Okay, so let's say for instance, itong given ko sa taas, di ba? Kani-kani akong gi-encircle. This shows structural isomerism, particularly positional isomerism. Kasi sa first structure, kaning encircled with kulay green, the position of the double bond is in between carbon 1 and 2. But on the second structure, yung position ng double bond is between carbon 2 na and carbon 3. Okay? The same molecular formula, but they differ on the position of the double bond. So that is not stereoisomerism kasi nakakaiba lang yung structure due to the order of bonding. Nasaan ba yung double bond? Okay, so particularly this is a positional isomerism. Pero pag sinabi namang geometric isomerism, this is something to do with the spatial orientation ng mismong alkene group. Okay, so dapat ang imong makita sa structure, puro, ayan, wait ha, puro mga alkene compounds wherein you can look at its trigonal planar nga orientation. So dapat nakita nimo ang double bond niya, ayan. Di ko pwede makasulat dire. Ayan, dapat makita nimo ang double bond carbons or carbon to carbon double bond nga naka-trigonal planar sila. Di ba nimo ma-distinguish ang iyahang specific type of geometric isomerism if wala naka-arrange in a trigonal planar orientation ang double bond carbons. Di ba? Kinaman tayo duha ka classification ng geometric isomerism. Pwede nimo siya ma-classify ang geometric isomerism being shown as cis-trans isomers or as E or Z isomer. So ay hara na nimo ma-identify ang yang specific geometric isomerism if ang double bond carbons naka-trigonal planar orientation. Okay? Akong pasabot sa trigonal or planar orientation. Yung carbon to carbon double bond yan, naka-trigonal planar orientation. Ibig sabihin, yung makita gid nimo ang bond nga 120. Di ba? Pag trigonal planar 120, ang kalayon sa mga bonded atoms. So, mana siya. Okay? Now, this time, for this afternoon, we will tackle the remaining types of stereoisomerism. Okay. So we have the second type. Let's proceed first with the conformational. Ayan. So for conformational isomerism, this is a type of isomerism wherein the structures differ. They differ on this structure because of the differences in conformation. So by the term itself, di ba? Kung mayroon kag conformation or shapes, conformation, shapes, ibig sabihin, arrangement na siya. We are focusing on the arrangement of atoms. So isomerism man, so nag-differ ang structure due to the differences in the conformation, differences in the arrangement of atoms, particularly in 3D. By the way ha, stereo na ta stereoisomerism, puros na siya three-dimensional arrangement of atoms. So conformations again, arrangement of atom or shape, simply shape of atoms. Okay, so different ang ilahang conformations. Now, the differences in the conformation, this may occur in the following. Okay, this may occur in an open chain compound or in a cyclic compound. So pag sinabing open chain compound, posible no ang conformational isomerism among open chain alkane compounds because of the ability of the single bond to rotate. Okay, so pwede na to pwede ta maka-provide og another isomer from an open chain alkane, okay, via rotating the single bond. Okay? Ang single bond, capable siya mag-rotate. Kay ano lang man siya, the bond is formed via end-to-end collision. So, dali lang siya ma-rotate kumpara sa double bond or triple bond. Okay? So, that's the reason nga nung ang alkane nga open chain, they are capable of forming conformational isomers. Cyclic compounds also, particularly mga cycloalkanes, they also are capable of forming conformational isomerism by flipping the ring. Okay, so let's start with the open chain compound. Paano yung conformational isomerism? Okay, so say for example, ethane. Okay, so ito yung pinaka-simplest example. By the way ha, again, ako siyang i-repeat. Dili na ko mo ipadraw gyud og mga structures ng isomers, may it be geometric, conformational, optical isomers. Ang inyo halang dire is for you to understand the concept. Okay? Para alam nyo how to identify, when to identify na it is conformational already, it is geometric, it is optical. Okay? So, conformational, again, it occurs among open chain. So, magsugod na sa open chain compound nga alkanes. Again, alkanes. So, example, si ethane. So, I know you're all familiar with ethane. Mo ni siya iyahang calculate structure, di ba? Ethane, dalawa yung carbon. So, yan yung chemical formula niya, C2H6. Ayan. C2, klaro man siguro, C2H6, dalawa yung carbon. Each carbon has 3 hydrogen surrounding it. Okay. Now, since we are talking about the three-dimensional arrangement, this is not yet the 3D arrangement, diba, of the central atoms ng ethane. This is not yet the 3D. Kasi if you try to check, each carbon has 4 electron groups. Kapag 4 electron groups, ano yung orientation or shape kapag 4 electron groups? Diba dapat naka-tetrahedral, and that is not a tetrahedral shape, okay, for a central atom carbon. So we have different ways, chemistry, we have different ways to draw graphically the three-dimensional arrangement of atoms ng mga molecules. Okay? So, daghan ta klase ng mga projection para ato ang ma-imagine ang 3D, ang three-dimensional visualization ng atoms in a particular molecule. So, say for example, we draw the ethane using the Sawhorse projection. Again, I will not let you draw a structure. Okay, let us just understand kay bakit conformational, capable siya mag-form og different shape. Okay? Now, this is the eclipse arrangement ng atoms for ethane using Sohor's projection. Okay? That is just ethane ha. That is just ethane. Kung imong lantawon, na ako ang wait sa ha. Magkuha sa ako og pen. Ayan. So, hinay, gid kaya akong net. Ayan. Okay. So, I will highlight the carbons for the for this structure ng ethane shown in an eclipsed nga way of arrangement. Okay? So, kanang highlighted with color red, muna siyang 2 carbons for ethane. Diba? 2 carbons of ethane. Then each carbon, tingnan, each carbon has 3 surrounding hydrogen. So that is just ethane. Pero, gi-represent lang ang structure in a 3-dimensional arrangement. Okay? Meaning, naka 3D. Ano ba yung 3D arrangement ng mga central carbon dito kapag 4 electron groups surrounding it? Diba dapat naka-tetrahedral? Now, if you try to analyze, diba naka-tetrahedral man yan? Naka-tetrahedral, approximately 109.5 degrees ang distances ng mga surrounding atom in a central atom, from a central atom. Okay? So, eclipse na siya, common sense, diba? Kung mingon kag eclipse is, na-alignment ang front to the back. Eclipse. Diba? So, di na ako na siya, emphasis kabaluman mo unsay kanang solar eclipse, di ba? Nag-align ang Earth, Moon, Sun, di ba? Munang eclipse. So, dere, ang eclipse, nag-align ang carbon to carbon, carbon sa front, carbon sa likod, hydrogen sa front, hydrogen sa likod. So, this is just the name of, specific name sa Sohor's projection. Okay? Now, this is not yet the conformational isomerism, ha? We only represent first its Sohor's projection via eclipse. Now, we can produce a conformational isomer out of this eclipse nga arrangement. How? Sabi dito, di ba sa open chain, we simply rotate a single bond. So, it's either nasa likod or nasa front nga carbon, imo siyang i-rotate. So, example, yung nasa likod, or nasa harap yung gi-rotate niya. Tingnan mo, itong carbon na to, this single bond has been rotated. Okay, may it be counterclockwise or clockwise. Diba, na-rotate siya. That is why this is not already eclipse. Hindi na eclipse, dili na magka-align ang hydrogen, surrounding hydrogens for each carbon. Naka-staggered na. Okay, so common sense lang, naka-staggered na after rotating the single bond. Okay, so this forms already a different shape, diba? Different shape, but of the same molecule. This is still ethane, tama? Same formula, same molecule, but they already differ in the 3D arrangement, tama? Nag-differ ang ilahang 3D arrangement. So that is conformational isomerism. Again, that exists among open chain compound if we rotate a single bond. Okay? So, between the two, if tinanong kayo sa quiz, between the two sino yung much more stable nga arrangement? Which do you think? Is it letter A or letter B? Which do you think is much more stable? When I say stable nga arrangement, dapat magkakalayo yung mga atoms, okay, para maiwasan yung um, repulsive forces kapag nagkadikit yung atoms. Yes, very good. Letter B, yung more stable. Okay, letter B yung more stable kasi staggered dili na karon magka-align ang mga kung kaning manggid siya kaning sa eclipse di ba magka-align ang hydrogen, so may possibility nga na repulsive forces, okay, that could affect the stability of the structure. Naalala yung sa when we identify the molecular shape, the geometry of the molecule, di ba? I always emphasize the VSEPR theory, the valence shell electron pair repulsive theory. Na as much as possible, dapat far away from each other ang atuang distances ng mga surrounding atoms para maiwasan yung repulsion. Kasi what surrounds an atom? Those are electrons. And electrons are highly negative to negative, pwede na siya mag-repel. Okay? So much more stable nga arrangement dito is the staggered one. Okay? Sige, let's have another projection. Okay? It is still ethane pa rin, but different projection. Different way ba to draw in 3D arrangement. Okay? Yung molecule nga, ethane. So let's have, for example, perspective nga projection. This is another way ha. Kuan lang ni siya ha. Another way to graphically draw 3D arrangement ng molecule. So another example is via perspective projection. Kanang imong own perception kung imong imagine nun ang ethane. Okay, nga naamoy backup knowledge nga it is in tetrahedral orientation. So ingani siguro inyong imagination as if inyong view is dire. So nag-align gihapon ang carbon to carbon and the hydrogens. By the way, kaning solid line, kaning sa baba, itong solid line, ibig sabihin niya nasa front mo yung atom, nasa front mo. Okay, pointing to you. Okay? Kapag dashed line, pointing at the back of the plane. Kanang straight line, kaning straight line on the plane. Okay, kung yun sa napag-draw, kani akong pagkasulat na siya sa plane. Okay, again, ang solid line sa any structure ha nga inyo ma-encounter, pointing to you, in front of you, then dashed line at the back. Okay, so kung inyo ang lantawon, try to check the arrangement of the surrounding hydrogens, di ba, they naka-align. Naka-align sila sa each other. Again, this is just ethane pa rin, so eclipse na siya. Eclipse kasi naka-align yung carbon and the surrounding hydrogen. Now, let's try to produce its conformational isomer. How? Paano ulit? For open chain, rotate. Rotate the single bond. Okay? So, pag-rotate, so in this given structure, given na representation, ang girotate is yung nasa likod. Okay? Na single bond. Okay? Ito. Girotate siya. So, tingnan mo ngayon, yung nasa baba ng mga hydrogen, nasa taas na. Okay? So, this time, hindi na naka-eclipse, hindi na naka-align yung mga surrounding hydrogen. So, this is already a staggered arrangement of the atom. So, conformational, nag-conform ka, nag-produce kog another conformation of an open chain compound via rotating a single bond. Okay? So that is another way, by the way, to represent the 3D arrangement of the molecule ethane. Perspective naman to nga, projection. But again ha, this is just ethane. Another way lang to represent its three-dimensional arrangement na naka-tetrahedral each central carbon. Diba? Tingnan mo yung each carbon, naka-tetrahedral. 109.5 degrees iyahang approximate nga kalayon sa mga surrounding atoms. So, ganun pa rin yung staggered, yung much more stable na orientation. Bakit ulit? Kasi preventive yung steric effect or yung repulsive forces affecting the stability of the structure. Sige, another gihapon ni siya nga way to represent the 3D arrangement of a molecule. So for ethane, pwede gihapon nato siya i-draw, i-represent iyahang 3D arrangement ng atoms via Newman projection. So yung Newman projection, this is actually the easiest or most convenient way to show the carbon-to-carbon bonds nga nag-align. Okay? So kaning in front, kaning front nga carbon, okay? Then kaning mga single lines nga imuhang makita, okay? Mo na siya ang first carbon, okay, for ethane molecule. So yung nasa likod, naka-align lang ana siyang likod, another carbon, then naapod siya surrounding hydrogen. So that is just ethane pa rin, naka-Newman projection lang. Okay, yung way to represent its 3D arrangement. So 3D arrangement pa rin yan. Okay, naka-tetrahedral pa rin yung central carbon. Okay, central carbon. So ito yung eclipse kasi obviously naka-align man, 'di ba? Naka-align yung mga surrounding hydrogen, and when we try to produce its conformational isomer, try natin i-flip, pwedeng yung nasa front, pwede yung nasa likod. Okay? That's why in your notes, ingani ang inyong makita. Di ba? Gi-flip. Ang nadiri, gi-flip ang yung nasa likod nga single bond. Ang nasa likod nga single bond, gi-flip siya. That is why naka-staggered na yung surrounding hydrogens. Ayan. So again, between the two, much more stable is the staggered positions ng mga surrounding atoms. Alright? So, ang point lang dire sa conformational isomerism ulit, type siya ng stereoisomer. Isa siyang type, specific type ng stereoisomer in which yung mga molecules, yung mga isomers, they can be interconverted by rotation. Okay? For open chain. Okay? For open chain compound. Again, we're talking about alkane lang. Alkane kasi, sila lang yung may mga single bonds. Okay? Dili capable sa conformational isomerism yung alkenes, alkynes, kasi they already have a rigid multiple bond. Pag sinabing rigid, dili gina siya ma-rotate. Okay? Dili gina siya ma-rotate. Okay? Ang multiple bond. So, single bonds, kapag alkenes, capable silang mag-form of conformational isomerism by simply rotating the single bonds. Okay? So, let's have the cyclic compounds. For cyclic compounds, di ba, close man ni siya nga chain. Okay? Cyclic compounds, close nga chain. So, for this existing conformational isomerism, ma-produce naman yung specific type of isomerism via flipping. I-flip na to ang ring. Okay? Kasi kapag cyclic, we are dealing here with different rings of molecules. Okay? Again by the way, cycloalkanes ni sila ang ato ang ma-encounter for cyclic compounds under conformational isomerism. Okay, so say for example, for cyclobutane. Okay, so this is the planar. Ano siya ang planar nga orientation for cyclobutane. Okay, nasa plane. Kanang imong gidraw ang cyclobutane in a plane sa inyong sa papel. Pwede raman ni madraw, di ba? Now, when we try to produce its conformational isomer, we simply flip. Okay, we flip a part of the molecule, cyclobutane, para much more stable yung molecule. Okay? So, ang nahitabuan ni, kani siya, nga part, kani nga carbon, and ang iyahang ka-opposite side nga carbon, i-flip ninyo siya down. Okay? So, imagine lang ninyo, gi-flip down, ang carbon imagine na magkuha mong papel, i-flip down ninyo siya, ingani iyahang structure. Okay, again nakakuha ni siya, naka-tetrahedral. Each carbon sa cyclobutane, apat diba yung carbon na yan, naka-tetrahedral shape. Kasi again, we're dealing here with the 3D dimensional, or 3D, redundant 3D arrangement of atoms in a molecule. Okay, so naka-tetrahedral yung mga carbons dito. Okay, for cyclobutane. Tetrahedral, ayan, tetrahedral. So, from planar, when you flip its ring, para mabuo yung isang conformational isomer niya, that will form butterfly conformation. So, wala na tayo mahimo, mao man gyud ang ilahang pagka-observe butterfly siya. Maybe because how it is, katong mechanism how it is being flipped. Diba, gipaubos siya. Kung imo siyang ibalik sa taas, mura galupad nga butterfly. Okay? Kung imo siyang i-flip paubos, balik sa taas, ubos back. So, mura siyang butterfly iyang orientation. Okay? Now, between the two, of course, very obvious nga much more stable yung arrangement ng mga surrounding atoms for a butterfly conformation. Again, that is simply because, again, to prevent the steric effect. Okay? To minimize the steric effect or yung bulky effect, katong repulsive nga forces that might affect sa structure ng molecule. Sige, another example. Sa cyclopentane. So, ito yung planar. Okay, mo i-draw ang cyclopentane in a planar orientation. Yan na siya. Diba, cyclopentane, 5 yung carbon. Diri lang, gipakita niya ang mga bonded nga mga hydrogens per carbon. So, obviously, per carbon dyan, merong tig-2 hydrogens. Okay? Now, if we try to produce its conformational isomer, flip lang gihapon. Yun yung sabi sa conformational isomerism. We can produce its conformational isomer for cyclic compounds if we flip a ring. So, pag flip ana, that will produce an envelope conformation. Okay, so very, kailangan yun ninyo i-activate inyong 3D visualization here. So, ganong na envelope mo na siya, ma'am. Let's say, for instance, kaniya akong i-highlight with color blue. Example lang ha. Actually, pwedeng any dyan sa cyclopentane. Okay? Kana akong i-highlight nga kulay blue. Makita ba? Wala pa. Okay, ayan. Kana nga part, imo siyang i-flip pataas. Monin ni siya. Okay? The same lang na siya ha, ani. The same na sila, envelope. Kailan man tag-envelope, di ba? Di ba ang envelope kay naman siya open, close. Okay, kung imo siya i-open, mo ni siya, naka-open siya nga envelope. I hope inyo hang na-imagine ha, naka-open siya nga envelope. Okay? So, envelope conformation. Okay? So, conformation, naka-produce kag another shape. Okay? Upon flipping a ring. Okay? A ring of cyclopentane. And constant ni siya ha, constant ni siya for cyclobutane. If we flip its ring, okay, in a 3D arrangement, you can produce a butterfly conformation. For cyclopentane, if we flip its ring, ang imong ma-produce nga conformational isomer is in envelope conformation or orientation. Okay? Then, again, this is much more stable. Then, for cyclohexane, so ito yung planar shape, okay, orientation ng cyclohexane. And we can produce 2 possible conformational isomer. Okay? The boat and the chair. Okay? So, alin na lang siya para inyong ma-imagine. Let's start with chair. Okay? Kaniya akong gi-highlight nga kulay blue ulit. Kaniya akong gi-highlight nga kulay blue. Okay? From its planar shape. I-flip nimo siya pababa. Okay? Muna ni siya ang chair. So, mura siya ing-ani kung ako lang siyang i-draw skeletally. Mura siya, ana lang. Gi-flip na ko ning kaning part. Diba? Kaning part, kaning color blue. Mo ni siya. Mo ni siya. Okay? So, gi-flip siya pababa. Maura ang gitando, gi-flip pababa. Okay? That is, diba mura siya chair. Lingkod ka dire, na tao. Malingkod, munang tail. So, chair. Okay, muniyahang sandiganan. Ana. So, para sa ila, chair siya. So, wala tayo mabuhat. Chair na siya nga, conformation for cyclohexane. Now, for both naman nga conformation for cyclohexane, yung dalawa, kaniya akong gi-highlight nga kulay blue from the planar nga orientation, kananduha ka na akong gi-highlight. I-flip pataas. I-flip siya pataas. Yan na yung boat. Muna siya. Gi-flip pataas. But again, following of course a tetrahedral orientation for each carbon. Kasi each carbon merong 4 surrounding electron group. So dapat ang makita nato sa ilahang conformation, each carbon naka-tetrahedral. Okay, following also the 3D arrangement yun ng mga central atoms. Okay? Now, between the two, question, which do you think is much more stable? Kanang minimal yung repulsive effect or steric effect. Minimal. Is it chair or both? Is it chair or both? Which do you think is letter A or B? More stable. Yes, yung chair. Okay, letter A, chair. Kasi, with both, tanawi ang both. Kung naa lugar substituent dire, example, hindi ito hydrogen. Let's say, for example, this is chlorine, an electronegative atom. Let's say, this is a chlorocyclohexane. So, what surrounds, di ba, a chlorine or electrons? So, kung mag-abay na sila somehow with a hydrogen, pwede magkaroon ng repulsive effect. Whereas, dire, so nara diri ang chlorine kung ingani ang orientation, di ba? Kaya naman sa ubos, gi-flip man pa ubos itong part na to. Okay? So much more stable yung sa chair kasi mas malayo, okay? Yung mga malayo yung distances ng arrangement ng atoms in the molecule of cyclohexane. So much more stable ulit ang chair nga conformation for cyclohexane. Again, these are constant. If you flip the ring of cyclohexane, pwede ka makaproduce of chair conformation or both conformation. Between the two, more stable yung chair conformation for cyclohexane. Okay, so kung ano yung na-present sa slides for conformational isomerism, yun lang yung aralin nyo. Okay? Ako lang gusto na inyong masabtan is, bakit nag-e-exist yung conformational isomerism sa ethane, sa mga cyclic compounds like cyclobutane, cyclopentane, cyclohexane. Okay? So, again, ang bottom line ani, pwede ta makaproduce og conformational isomer for open chain compound by rotating the single bond. By rotating the single bond. Pwede ta makaproduce og conformational isomerism among cyclic compounds by flipping the ring. Okay, flipping the ring. Okay, so this is still a type of isomerism. Okay, same formula for a given molecule, nag-differ lang sila sa spatial orientation, sa 3D, no? 3D arrangement of atoms. Again, same formula, same ang molecule. Okay, same ang molecule, but they differ on the spatial orientation. Okay. Now, let's proceed to the third type of stereoisomerism. We have the optical, or this is also known as the configurational isomerism. Okay. Now, when we say optical isomerism, this is a type of isomers that differ in the arrangement of atoms in 3D space, which creates a mirror images of each other. Okay? So, kailan man tag mirror images. Example sa mirror image is kanang magtanaw ka sa mirror. Diba? Kana imuhang both fingers. Kung imo na siyang iatubang nimo ang imuhang both hands. Okay? Iatubang nimo ang isa nimo ka palm, ang isa nimo ka palm. Mirror image na sila. Nag-align ang imong thumbs, imuhang different parts sa imuhang fingers. Okay? So, that is a mirror. Some example ng mirror image. So, the same thing with the optical isomerism. Type siya ng isomer wherein ang given ng mga structure, it shows mirror images. Okay? Mirror images. Ganun pa rin, naka 3D 3D arrangement. Okay? Now, for optical isomerism, yung mga structures may exhibit optical activity. Okay, they may exhibit optical rotation or optical activity. Meaning ng optical activity, which is a characteristic of those molecules that are capable of forming optical isomerism, that is the ability of the compound to rotate a plane polarized light either to the right or to the left. So pag sinabing ang rotation ng plane polarized light is to the right, we can identify that that structure is a dextrorotatory structure for its optical activity. If yung rotation ng plane polarized light is to the left, levo. Rotatory naman yung optical activity ng molecule na yan. Okay? Now, ma'am, how do we know nga nag-rotate siya to the right, nag-rotate yung plane polarized light to the left? Kailan natin masasabi na dextrorotatory? Kailan naman levorotatory? Of course, we cannot simply detect the optical rotation or optical ability ng isang molecule by just looking at the structure. Okay, so dili na ito ma-identify by just our naked eye. Lantawon lang na ito ang structure. Dextro ni siya. Okay, levo ni siya. No. This is only identified by equipment. Okay? So yung optical rotation, take note, yung optical rotation, may it be dextro ba or levorotatory ba yung rotation niya, that can only be determined by an equipment known as polarimeter. So take note ha, ang polarimeter, ito yung equipment, ito yung kailangan natin to measure the angle of rotation. Okay? Or the optical activity or the optical rotation ng molecule. Okay? In our laboratory sa pharmacy, we actually have a polarimeter. So, sad to say, dili na to siya magamit kay virtual man ta. But, puhon, siguro as you go sa higher years sa pharmacy, pwede nyo siya ma-encounter under quality control nga chemistry. Okay, so please ha, dumdumin, dili na to ma-identify by just looking at the structure kung dextro ba siya or levorotatory. Okay, yung specific na optical rotation niya. That is only identified by polarimeter. But, we can identify if ang compound, meron siyang ability to rotate optically. Okay, so pwede na ito ma-identify kung ang compound is optically active. Okay? So, balik ko na ko. Dili na to siya ma-identify kung dextro siya or levorotatory when it comes to its optical rotation. Kung to the right ba or to the left. Pero, kaya na to ma-identify by just looking at its structure if ang compound is optically active. If capable ba siya to rotate optically. Meron siyang nature or characteristic na optically active siya. So, one criteria is yahang chirality. Okay? Dapat yung molecule must have a chiral carbon center. Again, the molecule must have a chiral carbon center. So, what does it mean? Pag sinabing chiral carbon center, una, dapat yung carbon is in sp3, hybridized. Yung clue lang dito kapag sp3 hybridized, carbon, puro single bonds ang nag-surround sa iyaha. 4 na single bond. That is for sp3. Muna ang clue na to. For a carbon nga sp3 hybridized, dapat yung carbon, meron siyang 4 na single bonds. Puro single bonds. Okay? Plus, magiging chiral siya if naka-sp3 hybridized plus yung mga surrounding groups, different groups. Let's say, for example, yung nasa taas, hydrogen, yung nasa kaliwa, let's say, chlorine, yung nasa baba, methyl, yung nasa kanan, let's have bromine. Muna siyang pasabot, different groups. Okay, nakuha ba yung chiral carbon center? Naka-sp3 hybridized yung carbon and yung 4 na surrounding groups, different groups. Walang magkapareha. Dili pwede duha ka hydrogen, dili pwede duha ka chlorine, dili pwede duha ka methyl, etc. Okay? So that is for chiral carbon, one of the criteria para ma-identify nato, okay, pwede na siya optically active na molecule. The second criteria is dapat no symmetry. No symmetry element. Diba kung yung kag-symmetry, wala dapat siya identical nga elemento. Wala siya identical nga nature for that molecule. So, inyong, para mabalaan ninyo nga, iyang symmetrical character, inyo siyang hation ang molecule. So, you already have the molecule, the structure. Hation nimo siya, may it be pa-vertical halfway, or pa-horizontal halfway. Then, compare the both sides. Okay? So, in this molecule, chlorine man ang nasa kilid, bromine, so walay symmetry. Kung mo siyang hation pa horizontal, okay? Yung nasa baba is a methyl. Yung nasa taas is a hydrogen. Okay? So, walang symmetry. Diba? So, kung naa kayo makita ng symmetry, ang nasa taas, pariha, hydrogens, okay. Hindi siya pasok sa optically active na compound. So, mora ni siya ang pinaka-main criteria nato in order to identify if a compound is optically active. Dapat na siya chiral carbon center. Okay? And there is no symmetry element. Hation mo siya pa vertical or diagonal. Pwede mo siya hation diagonally. Horizontal or vertical. Dapat wala gyud kay makita nga isa ka symmetry, duha ka symmetry, tulo ka symmetry nga sides. Dapat wala. Okay? Now, how do we identify? Example na siya. Specific example. So, before na ko siya i-end, rin lang ta mag-end. Then, I will provide a pre-recorded video lecture for the continuation. Because we have another activity for the next session. Mag-quiz ta for Thursday. But, hindi ito included. Ang akong i-discuss karon dili included sa quiz. Katurang mga na-discuss na ako last time. Okay? So, say for example, magkano siya? The given structure, na siya central carbon in sp3 hybridized. Tama? sp3 kasi what surrounds it? Puro single bonds. 4 na single bonds. And with 4 different groups. Hydrogen, fluorine, bromine, chlorine, these are different groups. So, correct na yung first criteria. No symmetry? Yes. Kaya mo siyang hation, pa-vertical, or pa-horizontal, or pa-diagonal, wala kang makikitang symmetry element. Okay? Now, how do we identify the number of stereoisomers in a given compound kung optically active siya? Okay? By the way, once optically active, na-identify nimo ang molecule nga optically active, meaning capable na siya. Capable na siya of optical isomerism. Meaning, pwede ka makaproduce og another structure niya that is considered optical isomerism. Okay? So, yan yung way to identify the existence ng optical isomerism. You have to identify first if ang compound optically active ba siya. If yes, pasok sa criteria yung chiral carbon center, no symmetry element, posible nga pwede ka makaproduce og optical isomer niya. How do we identify the number of stereoisomer ng isang compound ng optically active one? Na siya formula. You simply use the formula 2n formula. 2, then superscript n. Wherein the n there, that is equivalent to the number of chiral carbon. Okay? So, say for example, sa given nga structure, kani nga given nga structure, pila man ang chiral carbon? Pila ang chiral carbon? Isa lang naman. Isa lang naman yung central carbon na chiral dyan. Di ba? Isa lang. So, ang imong i-substitute anang n, 1. So, 2 to the power of 1, di 2 lang gihapon. Meaning, pwede ka makaproduce og duha ka structure. Isa na to, isa na siya. So, dapat siya isa ka structure. Okay? And, syempre, iyahang ka mirror image. So, alam nyo na ano yung orientation kung naka-mirror image. Okay? Kung makakita kaging ani na representation, symbol, mirror na siya. Meaning, yung dalawang molecule na kinumpare, magka-mirror image sila. Imo lang silang iharap. Yan lantaw. Lantaw akong camera ha. Diba, you have the first molecule. Okay, yung nasa kaliwa. Kanang akong gilabel number 1. Kuha na siya sa plane. Then, iharap mo siya sa isang molecule. Ang isa pod ka tong structure nasa kanan, kuhaon mo siya sa plane, iharap nimo siya. Diba naka-mirror image sila? Ang bromine, imagine na, imo silang gikuha sa plane, gikuha ang akong gidraw. Okay? Kanang naka-represent sa slide. Kuhaonin mo siya sa plane, then imo silang iharap. Imagine na, gikuha nimo sila sa plane, giharap. 'Di ba magka-align ang bromine, magka-align sa taas yung hydrogen, magka-align yung fluorine, then nasa baba magka-align yung fluorine. So magka-mirror image sila. Okay, so that is how to distinguish mirror images between structures or molecules. Okay? So, balik ko na ako ha for this slides. Ako siyang i-wrap up before na ako siya i-end. For optical isomerism, listen, for optical isomerism, the structures, okay, or the molecule, the compound must be optically active. Okay, must be optically active. So, paano natin malalaman na optically active yung compound or molecule? Natay duha ka criteria. Una, it must contain a chiral carbon center. Okay? Bisan pila pa na, basta as long as naa siya chiral carbon center, meaning that compound is optically active. Okay? Then, second criteria, no symmetry element. Okay, no symmetry element. Now, you can identify the number of stereoisomers or optical isomers nga pwede mong ma-produce out of that optically active compound. You simply use the formula 2N. Okay? So, kung isa lang, so obviously, isa lang yung chiral carbon, isa lang yung chiral carbon, just like the given example, you can only produce 2 stereoisomers. And syempre, yung dalawang isomers na yan, dapat magka-mirror image. Okay, magka-mirror image sila. Okay, so that is one of the examples. Simplest example pa ni siya for optical isomerism. We have different class pa for optical isomerism. Okay, so I will just provide a pre-recorded lecture kay time naman good siya. Okay, dali na lang to siya, mga 10 minutes siguro. Okay. Sige. Do you have any question for the topic discussed today? Wala? Sige, if walay question, akong reminders muna for everyone on Thursday. By the way, kindly check the task sheet number 7. I already posted it sa homeroom Google Classroom. So, mag-quiz ta. Short quiz lang siya. All about structural isomerism. Diba? Under structural isomerism natay different types, 6 types. Kung lang siya, purely identification. You simply identify if the shown pairs or 3 molecules in each item, unsa ang ilahang unsay specific isomerism nag-exist. Is it positional ba, functional, nga na. For geometric isomerism, you have to classify if it is cis-trans, easy. Saan dito yung E, saan dito ang Z, saan yung C, saan yung trans. Yes, Ms. Tabia. Wala. Okay, so yun lang for your quiz, a short quiz on Thursday. Another optically active compound is tartaric acid. Now, tartaric acid, this is an organic acid that is naturally occurring in many fruits, say for example, among grapes. Now, this is the skeletal structure of tartaric acid. In order for us to identify the number of stereoisomers that we can produce from this compound, tartaric acid, we simply use the formula 2 to the power of n, wherein n, that stands for the number of chiral carbon, carbon center. Therefore, we have to find out first the number of chiral carbon center for this skeletal molecule of tartaric acid. Now, we only have 2 chiral carbon center for this structure of tartaric acid. Because again, criteria for a chiral carbon center, it has to be an sp3 hybridized carbon. Ibig sabihin, puro single bonds, okay, must surround that carbon, and it must have four different groups. Okay, so for carbon 1, this is not a chiral carbon because the carbon has a double bond. Again, pag sinabing sp3, dapat puro single bonds. Another, yung fourth carbon still have a multiple bond, a double bond. So again, this is not in sp3 but in sp2 hybridized carbon. So yung dalawang central carbon are said to be chiral carbon, carbon 2 and carbon 3. Okay? What surrounds these carbon, magkakaibang group of atoms. Yung isa, OH, yung isa carbon with an attachment of 2 oxygen, the other carbon that surrounds carbon 2 is a carbon with an attachment of an OH. And yung imaginary group dyan is hydrogen. Then for carbon 3, different group of atoms then surrounds it. Okay, so we have an OH group. Okay, an OH group for this carbon, ha. We have an OH group, we have a carbon with an attachment of O or oxygen, and another carbon with an attachment of an OH. Then yung imaginary naman dyan is hydrogen. Okay, so these are the chiral carbon center for the molecule tartaric acid. So overall, there are how many stereoisomers that can be produced from the compound tartaric acid using this formula? There will be total of 4 stereoisomer, 2 to the power of 2 kasi dalawa yung chiral carbon center for the molecule of tartaric acid. So, apat lahat. And the stereoisomers, okay, ng tartaric acid, we can best show or represent them using the Fisher projection. So, this is just a way or a representation of a structure of a molecule in a two-dimensional representation. So yung Fisher projection, this is usually used to represent carbohydrates. Okay, so this is how the Fisher projection of molecules or structures being presented. So ito yung first, isa sa mga structure or stereoisomer ng tartaric acid. This is just tartaric acid, ha. Ito yung carbon 1, di ba? Yung carbon 1, ito yun, carbon 1, highlighted with color blue. Yun yung COOH. Ito yung carbon 4. Carbon 4 is also a COOH. So these are just tartaric acid. Yung way they are being presented is in Fisher projection lang. Okay, so yan yung structure 1. And of course, yung mirror image niya, ng structure 1, that is the second structure. Okay, then another structure, we have this one, stereoisomer ng tartaric acid. And of course, yung mirror image ng structure 3. Again, these four structures are simply the stereoisomers for the molecule or compound tartaric acid. Okay, and they are being represented in a Fisher projection. Okay, now from these pairs of compounds being presented, meron silang relationship that exist. Okay, let's start with structure 1 and 2. If we try to observe structure 1 and 2, they are said to be mirror image. Again, structure 1 and 2 are said to be mirror images. Aside from that, they are also considered superimposable structures. Again, aside from mirror images, yung structure 1 and 2, they are also considered superimposable structures. Now, what are superimposable structures? Now, when we say superimposable, ibig sabihin one structure can be placed on top of the other structure, and then they still look the same. Again, superimposable yung dalawang structures if yung isang structure can be placed on top of the other structure and then they look the same. Okay, let's say for instance, example lang to ha. You have this plate, yung plato, let's say square nga plato. Yung isang plato, ganito yung pagka-arrange niya. Okay, but it is still square, no? Yan. Now, if you are asked if these two structures are said to be superimposable, you simply place the one structure on top of the other structure. Now, if you think a second structure, upon lifting this plate and then placing it on top of the structure, hindi naman siya superimposable. It cannot coincide with the shape of plate 1. If you think hindi nagko-coincide yung shape ng structure 2 sa structure 1, you can actually make an even number of rotations to that structure para ma-assure mo kung nagko-conform yung structure ng dalawa. Okay? If yung conformation ng dalawang structure remains the same, you can do rotation. Okay? Trial and error. I-rotate mo yung structure. Try natin kung mag-a-align na yung mga parts, yung shape ng dalawang structure na yan. Okay, that's the way how to determine if superimposable yung structure. Again, you simply lift that structure, okay, from that plane, and then you place it on top of the other, and then check if all the parts of that structure coincides or aligns with the other parts of the other structure. Okay, so let's try to apply that concept to structure 1 and 2. Bakit naging superimposable yung structure 1 and 2? Try to check structure 1. Okay, yung structure 1, yung nasa left side na branches niya, OH. Okay, nasaan yung OH? Doon lang sila nagkakaiba, di ba? Sa structure 1 and 2. Yung OH naman ng structure 2 nasa right side. Okay? Now, how can structure 1 or structure 2 are said to be superimposable to each other? Now, we simply make a rotation to either of the structure. Let's say, for example, sa structure 1. Yung structure 1, we rotate it mga 360 degrees ng rotation. Okay? So, ibig sabihin, itong part na to sa baba, okay, i-rotate mo siya papuntang taas. Okay? So, what will happen, itong OH, okay, mapupunta sa kaliwa. I mean, sa kanan. Then, the hydrogen mapupunta sa kaliwa. Okay? Now, if you try to imagine the rotation, what will happen now, ang magiging itsura na ng structure, it will now become COOH pa rin yung nasa taas kasi magkapareha lang naman. Then, OH will now be seen on the right side. Diba? OH. Then, hydrogen on the left side. Now, if you try to lift again, lift structure 1, i-lift mo siya, then ipatong mo, i-place mo siya on top of structure 2, all the parts, no, of structure 1 will now coincides with the parts of structure 2. Okay? Kumbaga, upon placing one structure on top of the other structure, they will now look the same. Diba? So structure 1 and 2, aside from they are mirror images, they are also superimposable structures. And what do we call if a structure shows superimposable mirror images. They are said to be mesocompounds. Again, yung dalawang structure, kapag mirror image sila plus superimposable structure sila, these are mesocompounds. Meso, ibig sabihin, the same. So, same compound lang yan. Okay? Same compound lang. Nagkaiba lang yung orientation nila upon representing their stereoisomers using Fisher projection. So, same compound lang yan. Kasi nga, they show a plane of symmetry upon rotation to 360 degrees and then placing one structure on top of the other structure. The structures still look the same. That shows a plane of symmetry already. Diba? Therefore, if we try to go back on the criteria in identifying if a compound is optically active or not, mesocompounds are said to be not optically active. Ibig sabihin, optically inactive sila. Okay, so for structure 1 and 2, they are mirror images, superimposable. Okay, now for structure 3 and 4, yes, mirror images din sila, but this time, they are non-superimposable. Okay, mirror images pa rin. Okay, we already know how to identify mirror images. Pag sinabing mirror images, you simply lift both structure, then iharap mo sila. Okay, i-lift mo, kunin mo siya from that plane kung saan siya nag-draw. Imagine, mo siyang i-lift ng structure, then iharap mo siya. Parang dalawang kamay mo. Okay, iharap mo yung dalawang kamay mo, then they are mirror images. Okay, then pag sinabi namang superimposable, i-lift mo yung isang structure. Then ipatong mo. I-place mo on top. Huwag mo siyang iharap upon placing. I-lift mo lang. Okay, same na orientation niya. Upon lifting, same orientation. Okay, then place it on top. Okay, trial and error. If ayaw niyang mag-coincide, try to do a 90-degree rotation, 180-degree rotation, or 360-degree rotation for that structure until it will now coincide with the other parts ng isang structure. Pero kapag wala talaga, upon placing on top of the other structure, both structures still do not look the same, non-superimposable na yan. Okay, so say for example, yung structure 3 and structure 4. Now, kapag ang compounds or structures are said to be non-superimposable mirror images, each of that structure, they are called enantiomers. Okay, enantiomers. Okay, again, pag sinabi enantiomers, mirror images but non-superimposable. Okay, so try nyo ha, i-lift mo. Kung pag mirror images, i-lift mo sila, iharap, obviously mirror images, kapag hinarap mo siya mirror, dito sa mirror na to, magka-mirror images yung mga branches, yung mga chiral carbons, etc. Okay? Pag non-superimposable, kahit anong rotation na gawin mo sa isa or yung other structure, then i-place mo on top of the other structure, walang magko-coincide na part. Okay? Kahit anong gawin mo na rotation, even number of rotations. Okay? Walang magko-coincide na part, non-superimposable. Now, for enantiomers, take note, enantiomers, we can actually identify if a chiral center of that enantiomer is an R or S enantiomer. Okay, so we have two subtypes of enantiomer. Okay, this is actually a label for the chiral center of enantiomers, if R or S. Now, R or S enantiomer, or RS, that is an approach or a system by which we use the principles of Can-Ingold pre-log rules. So in this system, we simply assign the groups, the surrounding groups of each chiral center based on priority. Okay? Again, yung RS That is according to a system by which its substituents for that chiral center are assigned with a priority number. Okay, so how do we assign priority for each surrounding atoms ng chiral center? We simply base it on the atomic number of the atom. So same principle with the E and Z isomerism. Di ba? Na-mention doon yung can-in-gold prelog rules. We simply determine which group of atoms ang priority based on highest number of atomic number. Okay. Now, for identifying R or S enantiomer, we can only determine its label or its specific enantiomer for the chiral center if the structure is in 3D, okay, 3D orientation. Well, I have said earlier, Fisher projection is in 2D, two-dimensional orientation. So let's have the 3D orientation of tartaric acid. So this is the 3D orientation of tartaric. This is still tartaric acid ha. Tartaric acid lang to. Again, sa tartaric acid, merong 4 na carbon. Carbon 1, 2, 3, and 4. Okay, carbon 1, 2, 3, and 4. Naalala, yung carbon 1 is COOH. COOH ang carbon 1 and 4. Carbon 2 and 3, sila yung chiral center. Therefore, we only identify the RS sa chiral center. So, unsaon man nato pag-identify if R enantiomer, S enantiomer. Okay, let's have structure 1 first. So, na naman siya label. So, R na siya, R enantiomer. Bakit naging R enantiomer? Okay. Now, sabi kanina, by the way, bakit pala, kailan pala R? Okay? Kailan S enantiomer? Okay? Now, pag sinabing R, ibig sabihin yan, rectus, ibig sabihin, yung direction of priority group assignment is going to the right or going clockwise. Okay? Kumbaga, upon assigning the priority group that surrounds a chiral center going clockwise yung assignment, okay, then that is an R enantiomer. If going counterclockwise, kailan tag clockwise, no? Kanang kung unsa ang tuyok sa clock, no? Sa orasan. Clockwise, diba, to the right. Okay, so R clockwise, counterclockwise naman if S. Sinister yung pinanggalingan ng letter S dyan. Okay, sinister. Clockwise. Okay. Now, bakit naging R enantiomer yung first structure? Okay, di ba? Ito yung chiral center. Okay. First chiral center. Check natin. Okay. Yung first chiral center, yung surrounding groups niya, okay, which are different groups kasi kapag chiral center, different yung group of atoms na nagsusurround per chiral center. So, obviously, ang nagsusurround sa'yo na atom na directly attached, atom na directly attached to the chiral center being encircled with color red are the following. We have a carbon, an oxygen, and another carbon. Okay? Well, for these two carbons, these are considered two different groups, no, surrounding this chiral carbon kasi itong carbon na to, yung attachment niya is OOH. Whereas this carbon, okay, on the right side, yung naka-attach sa kanya, OH. So, magkaiba sila na group attachment. Now, if we rank these three, syempre hindi na natin i-rank yung hydrogen kasi hydrogen can never be a priority group. Now, if we try to rank the group of atoms that surrounds the first encircled chiral center, yung first in highest priority based on atomic number is yung oxygen. Diba? Between oxygen and carbon, yung may highest atomic number is oxygen. So siya yung rank 1, followed by a carbon with 2 oxygen. So this would be rank 2 based on priority. That's can in gold, diba? Can in gold prelag rules. We rank the attached na group of atoms from the central carbon based on highest atomic number. So, between these two carbon with an OOH and a carbon with OH lang, mas higher rank yung COOH. Okay? Then, obviously, ito yung rank 3. Okay? Now, if we try to check the direction of the assignment of priority groups, it is going where? Going clockwise. Di ba? Mula dito, going clockwise. Okay, going clockwise. So, siya kurasan. To the right. Kaya R, enantiomer siya. Okay, R, enantiomer. The same goes with the other chiral carbon center. Kapag sa isang enantiomer, yung isang chiral carbon center naka-R orientation, automatic yung isa din R orientation. Hindi pwedeng sa enantiomer, sa may isang chiral center na magkaiba yung direction ng priority group assignment niya. Okay? So you can double check the second chiral center for this structure 1. Okay? So for structure 1, check natin yung pangalawang chiral center. Okay? So erase lang sana ako ni ha. Check lang nato if R ba talaga. Okay? Naka-clockwise yung direction ng priority group assignment. So ito ulit. Itong encircled with color blue, that is another chiral center. Again ha, yung R and S, so that is a label. Label yan natin for the non-superimposability of enantiomers. Okay? Sige. So, for the second chiral center, so una ulit, priority yung oxygen, followed by yung carbon with an OOH, and pangatlo yung carbon with an OH. Okay? So, ayan. Again ha, when you rank the surrounding atoms, yung mismong directly attached, okay? Yung mismong directly attached sa chiral center nga imuhang gina-determine kung R ba siya or S enantiomer. Okay? So, ayan. So, if you try to check the direction ng assignment of priority group, it's going 1, 2, going clockwise din. Diba? Going to the right pa rin. Okay? Going clockwise. Clockwise. Okay? So, R enantiomer. Next, sa second, okay, structure 2, ito naman yung S enantiomer. So, check natin. Okay, per chiral center. Per chiral center ka mag-check. Okay? So, yung first encircled chiral center, i-rank nato ang iyang surrounding group of atoms based on atomic number. So, ito yung rank 1. Rank 2, carbon with an OOH. Rank 3, yung carbon with OH. Okay? So, tingnan yung direction. Carbon 1, highest priority. Then, pababa, going counter. Diba? Opposite siya nga direction sa structure 1. Going counterclockwise. Okay, pabaliktad sa orasan nga tuyok. Okay, the same with the other, okay, with the other chiral center. Sorry. Okay, so example, this one, naka-S, S enantiomer din yan because, di ba, ito yung highest priority, second, and third priority. Okay, so yung rotation, ayan, going counterclockwise. Alright? Sige, let's have another example. Again, you can only determine if the RS enantiomer if naka three-dimensional orientation yung structure. Alright. So for this given example, obviously, isa lang yung chiral center. Okay, between the two, ang chiral center is yung may apat na single bond. So, itong may asterisk. Yung may asterisk, yan yung chiral center. Yung isang carbon, itong carbon na to is not a chiral one. It is not a chiral center because again, it carries a double bond. So, it's not sp3 but sp2. Okay, now let's try to check if it is an S or R enantiomer. Okay, so for the structure 1, rank natin yung surrounding group of atoms for this carbon. Obviously, rank 1 yung nitrogen. Okay, between these carbons plus a nitrogen, syempre nitrogen yung rank 1. Then, between these two carbons, carbon with hydrogen and a carbon with an oxygen attached, highest priority ito. Okay? Then followed by CH3. So yung rotation going counterclockwise, counter. Inyong halang basihan is ang tuyok sa orasan, di ba? So pabaliktad siya, counterclockwise S enantiomer. So obviously, ito, yung mirror image niya is yung R enantiomer. Okay? Rank 2. Diba? Ito yung chiral center. Ang imong i-rank is katong directly attached to that chiral carbon center. Then rank 3. Okay? Ayan. So, clockwise naman ito. Okay, clockwise. Okay, for the other example, isa lang naman yung chiral center. Okay, so madali lang siya i-rank. So this would be rank 1, this would be 2, and rank 3. So you know already bakit rank 1, 2, and 3 yan. Based on atomic number. Okay, based on atomic number. So this is counterclockwise, so S enantiomer. Okay, ito naman naka-counterclockwise. So, clockwise. Okay, R enantiomer. And lastly, we have the S enantiomer, and the other one is an R enantiomer. Okay, so this one is an R enantiomer kasi, again, the direction of priority group assignment is going clockwise. So, ito yung rank 1 based on atomic number, rank 2, rank 3. Okay? So, clockwise siya. Diba? 1, then 2, 3. Clockwise yung rotation or yung direction ng assignment. Okay? Dito naman is pa-counter clockwise. Diba? Ito yung rank 1, 2, and 3.